I'm Jeff Rosenfeld. I'm the editor of the Bulletin of the American Meteorological Society, and I'm here with Tom Bogdan, who's president of the University Corporation for Atmospheric Research. And UCAR is an important entity for many, many different reasons in our community. I'm here to talk with Tom right now about space weather, which happens to be your field. I'm not even sure exactly how you got into that. You could just give me a little background there.
Well, space weather is a very exciting new area of activity, and it's something that the American Meteorological Society has been thinking about for a long, long time because of many of the parallels that exist between space weather and terrestrial weather. Most people probably don't know what space weather is. All of space weather starts at the sun and makes its way towards Earth, and many of the other planets actually are subject to it. But what's making it a topic of excitement these days is the impact that space weather has on many of our important technological systems. People often go, why am I only hearing about space weather now? I mean, when did it start? Actually, it started billions of years ago when we saw the aurora borealis or the aurora australis. We were seeing space weather, but that wasn't such a big deal. But over the last 100 years, we've put in power grids, we use GPS for finding our locations, we use satellites for communications and emergency response, and all of these high-tech systems are subject to the impacts of space weather that come from the sun. And that's what's created of late a lot of excitement about space weather and a lot of focus in the research and operations side to create the types of forecasts and outlooks that emergency managers and national security staff need to ensure that we safeguard those capabilities.
It seems like a very exciting time for space weather scientists at this meeting because you got an upcoming launch, right?
Yeah, we do, of Discover.
Maybe you could tell me a little bit about what that could do for us.
Exactly. Well, let me take a step back and say that the space weather comes in 3 different flavors, if you will. And Discover is going to help us with one of those critical flavors. So the sun will shoot out blasts of X-ray radiation, photons, short wavelength, that ionize the ionosphere, the sun-facing part of the Earth's ionosphere, and that impacts GPS and communications. That's one of the 3. Discover's not aimed at that. The second are showers of energetic particles that come from the sun. Those particles travel rapidly through space. The photons take 8 minutes to get from sun to Earth, and when they're here. 30 to 40 minutes for the energetic particles because they're traveling at a fraction of the speed of light, and their impact is on satellites. Essentially, the electronic brains of satellites can get confused when there are hits of these energetic particles on their very delicate circuitry. But what Discover is up there to do is to deal with the third of these aspects. From time to time, the sun ejects large parts of its outer atmosphere in sort of a tremendous astronomical tsunami that leaves the sun and propagates out through interplanetary space. And if the Earth happens to be in that path, that can lead to the impacts on our power grid, because that big wave of plasma bashes into the front side of the Earth's magnetosphere, and it causes magnetic field fluctuations down at ground level. What Discover does is it's a sentinel. It sits about 1% of the distance between sun and Earth, that's where it will sit, and it will measure and detect this incoming tsunami. Now, the big ones, the ones that can have a huge impact on our power grid, take about 20 hours to make that transit from sun to Earth. 1% means we've got about 20 to 30 minutes of lead time. And that's enough time for power grid operators and emergency managers to do the sorts of things they need to do to protect their sensitive power grids. And that's what Discover will be doing for us. It's our sentinel in space.
Now, does this new ability in terms of observing change other aspects of the space weather enterprise in terms of modeling and preparedness activities?
Space weather is where terrestrial or conventional weather was back in the end of the 1950s. We're now starting to put some of our first space weather forecast models online. And these take place at the National Oceanic and Atmospheric Administration Space Weather Prediction Center, which is based in Boulder, Colorado. And it is the nation's source of space weather. It's actually in the National Weather Service. So the National Weather Service really goes from the sea to the sun in terms of looking at its impacts. The first models that are there are looking at the propagation of these events. Not all of these tsunamis will have Earth in their path, and not all of them will be effective in having big impacts. And so their models take data from many observational platforms. Discover will be one of them, but many of the NASA satellites are used as well. And they put it into a model that simulates that coming out. If you think about hurricanes, often we have this kind of cone of where the hurricane is going to go that we see often. In space, it's a cornucopia. It's like a horn, a Victrola horn, that this model computes. And if Earth is in that cone, then alerts go out and people are notified of it. But if it's not, then we don't put any false alarms out there.
Now, what do the space weather forecasts look like, or what will they look like in the next 5-10 years as this new capability comes into play? It seems to me that there's some talk at the meeting, at least, about regional forecasts as opposed to, say, global forecasts of these phenomena. What does that mean? What does that kind of look like?
Absolutely. The impacts on the Earth vary from region to region. The biggest impacts of the geomagnetic storms that come from these tsunamis typically is felt at higher latitudes. The northern tier states of the U.S., Canada is subject to those impacts. Also Europe, Scandinavia. But during big storms, those impacts can move south. In fact, the largest storm we know about historically is in 1859, and at that time, people here in Phoenix at this meeting would not have seen the aurora borealis because it was south of us. It was south of us. Normally it's north. People in Havana, Cuba saw that aurora borealis. That's how big that impact was. And so regional forecasting will help people to not respond to global alerts when there's not impacts that are going to occur to them. So looking regionally is important. It's particularly important for GPS. GPS outages can be regional. During extreme storms, loss of lock on satellites and GPS is possible, and you may be having a natural denial of GPS service. You can imagine, for a variety of reasons, it would be nice to know if that's going to happen in advance. If you are doing drilling on oil rigs in the Gulf, you have to position those very accurately. If there's going to be a day where you don't have good accuracy, you don't want to be working.
Now, obviously, observing capabilities and then modeling capabilities are a big part of that sort of total system of alerts. What about research questions that still remain that maybe will be resolved with newer satellites?
There are many key research questions, but one of the ones that I think keeps a lot of people working very hard is that, like we have seasons of weather activity on the Earth, the sun has seasons as well in its weather activity. It's called the solar cycle, and ours is a year, of course, but the sun's is about 12 to 14 years, depending on the length. It has a period where it's very active, and it has a period where it's fairly quiet. We're now coming out of the top of an active period for the sun. Each year is different than the next, just like sometimes we have a more difficult winter than other winters, same as with the sun. This last cycle has been fairly quiet as far as cycles go, but previous ones back in the 50s and 60s were tremendously impactful. And in 1989, a space weather event took down the grid in Hydro-Quebec in Canada. So some of them can have more impacts than others. People who are putting satellites up into space, people who are planning for various events, want outlooks as to how severe space weather is likely to be. It tells them how much shielding do they have to put up to guard their intelligence on those satellites and how they want to react to it.
Now, what is satellite drag? That's another topic that comes up quite a bit at the meeting. Maybe you could explain what that is.
When the X-rays come in, they not only ionize the material, but they heat it up. They dump their energy there. And so the atmosphere kind of breathes out and expands with that heat. That causes drag on small debris that is up at these higher altitudes. And that's a good thing, actually, because all those small pieces of debris that are there from defunct satellites, satellites that have blown up in space, are dangerous shrapnel for the existing satellites. So we want to clean them out from time to time. As they encounter more drag, they drop in. They encounter even more drag as they drop in, and then they become a fireball and are cleaned out. So there's a natural cleaning process of the debris. The weak solar cycle we've had is problems for satellite operators because we haven't cleaned out a lot of that debris, and as you know, more and more of it ends up there all the time.
Now, and one last question, obviously space weather is something that some people sort of feel is disconnected to terrestrial weather in the traditional sense of the movement of the atmosphere. Are there any connections between such things as thermosphere expansion and what we see in the troposphere or, say, the stratosphere?
It's an area of really intense research. There are a lot of indications that there are correlations between things the sun does and effects that we see in our weather and climate. No one has really identified a good mechanism for that coupling, but there's always tantalizing correlations and activities that people are looking at. In fact, back in the early parts of the 20th century, space weather research began in the Department of Agriculture because of the thought that if the sun and its variable output and influence can lead to predictions of droughts, that would be important for the farmer. Many years later, we're still debating whether there are those impacts or not.
Well, Tom, thank you very much for that overview, and look forward to learning a lot more at the conference about space weather.
Thanks.
Thank you.